All right. What you want to do is take a look at the fluorescent lamp, and what you see through the little spectroscope is you see the light spectrum of the fluorescent lamp. What you should see through for the light spectrum of the fluorescent lamp is kind of a rainbow of colors with some bright lines of light. Do you see the bright lines of light?
The numbers are supposed to look blurry?
You could kind of focus it, the numbers, if you want. Playing around with the other side.
I still got a small number.
What was your number?
0.89.
0.89. Maybe. You know, okay, did anybody get this? Did everybody give up? Wow. And just look how much time you burnt right there. If you had a 50-minute exam, boy, that was like a lot of it already, right? And so, you know what? I'll tell you, the people who know this, the method of successive approximations, would have been just light years ahead of you. Because that's how I would have solved this. I mean, the algebra is too hard. And so I would have just said, okay, the algebra is too hard. We're just going to guess and check it. And so to guess and check it, well, let's plug in some numbers here. So if I plug in some numbers, I'm going to get 1. All right, then I'm going to solve, n is 6, so that's 36 times 3.658. And so I'm just going to multiply. I'm going to ignore the units as long as I got the right actually, 36 times 3.658 is 131. So this is 131.688 over v squared. And then this is going to be v minus nb. So n is 6, b is 0.0429. So 6 times 0.0429. This is 0.2574. Is that right? Yeah. All right, this is going to equal nRT. So n is 6, r is 0.08206, and then I have to convert it to bar, 1.01325. Okay, thank you. 148.742. Okay, we'll do that. All right, now what I'm going to do is I'm going to guess a V, plug it in here, and see if it matches 148.742. But the problem is, what do I use for my first guess? You know, what I'm going to use for my first guess is I'm going to just use the ideal gas law. And so for my first guess, let's see, the ideal gas law says V is equal to nRT over P. And so let's go ahead and calculate that.
That's 148.74.
Okay, divided by 1. And so it's going to be 148.742 is that. All right, so, but I don't want to put that in there. So, because there's too many digits, I'm going to go, I'm just going to round this to 149. And so my first guess for V is I'm going to guess V is equal to 149 because the fewer digits I punch in the calculator, the better, the quicker. So if I do that, I'm going to go this. I'm going to go 131.688 divided by 149 squared equals plus 1 equals times parentheses 149 minus 0.2574. Close parentheses. And if V is equal to 149, then I have 149.6 is equal to 148.742. Is that a good match? No. That's not a good match. So should I go higher or should I go lower?
Lower.
Let's go lower. I'm going to go down to V is equal to 148. You know, because I don't want to add decimals in there yet. And so if I go V equals 148, then I'm going to do this. I'll just do this term first. If I do this term, I'm going to get 131.688 divided by 148 squared
Should be 147.
plus 1 equals times parentheses 148 minus 0.2574 close parentheses. And I get a little bit closer. I'm 148.63. 148.63, I'm getting close to 148.74. My target is 148.74. And so, where should I change it to?
148.001.
Too many. Let's just go. You know what I'm going to do? It's so close to this. I'm going to go V is equal to 148.1. Let's try that. And so I'll do this 131.688 divided by 148.1 squared equals plus 1 equals times parentheses 148.1 minus 0.2574 close parentheses. And I get 148.73 is equal to 1. Wow, getting close. Just that. I just want it to be just a little bit bigger. So what should I do?
148.15.
All right, let's try that. You want to try B equals 148.15?
Yes.
Okay. We're going to go with that. So let's do 131. I do this on the computer. It'd be much faster, but it's okay. We have a little bit of time. 138.688 divided by 148.15 squared equals that plus 1 equals times parentheses 148.15 minus 0.2574 close parentheses. 148.779. That's a little bit too big.
Exactly. It's 1.48.1.
Okay, how about that? Volume equals 148.11. 12? What do you think? 12 or 11?
1.
All right, let's try 11.
1.
All right, so I'm going to go with 131.688 divided by 148.11 squared equals that plus 1 equals times 148.11 minus 0.2574. Ooh, look at this. 148.740 is equal to 148.74. We got it. Although, to be honest, I would have went 1-1 before going to 1-5. No, just joking. I don't know what I did. But I was thinking 1-1. Anyway, we got it. How long did that take?
Almost 30 minutes.
It took almost an hour.
It took almost an hour, but we got an answer. The other thing is, how if I gave you another hour, would you have gotten an answer? No. And so think about what huge advantage just learning this simple method in Appendix A is. That's a tremendous advantage for you. Right? Well, anyway, what was it? Ideal gas. Remember, for an ideal gas, it was, what was the volume that we calculated for ideal gas? 148.742. For real gas, CO2,
It's
148.74. Was it worth it to do all that work
That's 148.1.
for this? The only difference between the ideal was the ideal gas, right, versus ideal. And so, okay, actually it was this. The volume is 148.11. For the ideal gas, what was the count? It was 148.779. And so if we assume it's ideal, the volume is 148.779. By using van der Waals, it came out to 148.11. And so van der Waals is more accurate. But was it really worth it? It was totally worth it? What kind of error would that have introduced? It would have been 0.6 to 0.7 liters difference. That's much less than 1%. And so maybe we could live with 1% error and save ourselves a lot of time. But anyway, that's that. And then, when we calculate the volume of the liquid, the volume of 2 moles of liquid water, we would use the more accurate density. And so 2 moles of water would be 36.04 grams of H2O. And the density of water at 298 Kelvin, do you know what the density of water at 298 Kelvin is? 0.9970. And so we do this 0.9970 grams per milliliter because we're going for accuracy now, right? And so we go for accuracy, and it's going to come out to this I got out of the table. And so 36.04 grams is the weight of 2 moles divided by 0.997, which is 36.148 milliliters. Versus, what do we normally use for the density of water? 1.0. If we use 1.0, then we got 36.04 milliliters. And so, is that really a huge difference? When we're talking about liters, this is nothing. And so, yes, it's more accurate if we use the real gas law instead of the ideal gas law. But think about the work. It was too much work, right? And therefore, sometimes what we do is we sacrifice a little bit of accuracy to make the calculation easier. And that's exactly what we do there. Sometimes we don't have the density and we just use the one we memorized, 1.0, but that's not always accurate because the density changes with temperature. And we sacrifice some accuracy there. But it turns out, and I'm not going to have enough time to do this, it turns out that the difference in joules is negligible. And so we're okay doing it the way we were doing it and not going super accurate. Okay? All right, now I'm going to stop here. What we're going to do is we're going to do a